flux describes the amount of a given quantity that passes through a given area. So for example, if we visualize these vectors representing the velocity of different particles of fluid, then the volume of fluid that flows through this area per unit time is the area by the velocity. So this gives units of volume per second, which is the volumetric flux, or the volume of fluid that flows through this area per unit time. And if we multiply this by the density of the fluid, we get the mass flux. So density by area by velocity will be mass per volume. So for example, kilo per cubic meter by meters cubed per second, which will give units of mass per unit time, which is the mass of the fluid that flows through the area per unit time. Now if we consider these vectors to be electric field vectors, then the electric flux is defined as a dot product between the electric field vector and the area vector. So for example, for this vertical surface, we have the unit vector that's normal to this surface, pointing in this direction. So the area vector is just the area by the normal vector, where the normal vector is a unit vector. And this form of the electric flux is for the case where the electric field vector is constant across the area. So noting the dot product can be written as the product of the magnitudes of both vectors by the cosine of the angle between them. So in this first case, where the electric field and the normal vector are parallel, then you're going to get the maximum electric flux through that area, because the cosine of the angle between them, being 0, is 1, which is a maximum. Now in this case over here, where the orientation of the surface is oblique, so the normal vector and the electric field vector are not parallel in this case, then more of the electric field is going to pass through this surface compared to this one. So as we've seen, the direction of the area vector is perpendicular to the plane of the surface, and it points outwards from a closed surface. So for example, if we look at this spherical surface, then the area vector is going to point outwards from this surface. If we look at different parts of this surface, so the sign of the flux is given by the dot product of the electric field vector and the area vector. So in this case over here, the flux is positive because the electric field vector and the area vector point in the same direction. And the same for this case, because the angle between the electric field vector and the area vector is less than 90 degrees. So both vectors point in the same direction. And note that under electrostatic conditions, this electric field is static, so it's not really flowing through that surface like a fluid. Now in general, the total electric flux passing through a surface is defined by the surface integral of the electric field over the surface. So here for example, we're looking at the area vector for a differential element of area. Now in the case of a sphere, you can imagine the electric field at different points on the surface of this sphere is constant. So remember that it was equal to the charge on 4 pi by the permittivity of free space, and inversely proportional to the radial distance from the charge. So in this case it's constant, where r is the radius of the sphere. And given that this electric field is always parallel to the area vector on the surface of the sphere, then cosine theta will be 1, and we can write the dot product directly as the product of the electric field and the area of the sphere. So the area of the sphere is 4 pi r squared. So therefore the electric flux through the surface of that sphere is going to be the charge on the permittivity of free space. And we're going to look at this more closely when we look at Gauss's law, where this charge is specifically the charge enclosed within that surface.